We'll finish up our discussion on coherent light wave systems. So last time we saw the different modulation formats, the basic principle of coherent detection, and how it can help boost the SNR or improve the receiver sensitivity by going into the short noise regime, right? And then we discussed these two main types of so we discussed homodyne and heterodyne detection, and then also synchronous and asynchronous detection. So now let's look at sort of the performance that we can get using these different detection schemes with different modulation formats, and fundamentally how the so again, we are ultimately interested in the BER performance of a link, right? So that's the metric we'll be using. So, or the receiver sense to obtain a certain BER. So let's first look at synchronous receivers, right? So recall our discussion from last time. Synchronous receivers were a bit more complicated. They required this carrier recovery through an electrical phase lock loop. But basically what one could do with synchronous receivers was to eliminate one of the quadratures of the noise, right? So we saw that, so we have this in phase which goes as the cosine omega t, and then the quadrature phase which goes as sine omega t. And basically using this carrier recovery and then followed by a low pass filter, we eliminate the quadrature phase, right? We have only one of the in phase component remaining. So basically the final sort of baseband current that we get, so we derived this last time, basically is the sum of, so this is the photocurrent from the photodiode, right? So this is the signal current that we're interested in. So again, so this depends on the signal power. And then we have the noise of the in-phase quadrature. Okay, so right, so now let's look at the different modulation formats, starting with ASK, amplitude shift scheme, which for all practical purposes is basically like intensity modulation, right? But now we're looking at the performance using coherent receiver instead of direct detection. So maybe to make this more specific, I'll write here. So this was the cosine, the in phase component went as the cosine of this phase, right, which was the phase difference between the sort of the signal and the local oscillator. And so the other quadrature Q component goes as sine phi here, right? So that is eliminated in our synchronous receiver. So for ASK, of course, the phase is not important, right? The phase is, we encode information in the amplitude, so only the IP components here, right? So that depends on, so for bit 1 and bit 0, so let's say for again, so the ASK modulation format, right? So let's say the amplitude here is A1 for bit 1, which is sort of square root of P1, and then for bit 0, A0 is just 0, right? So the signal power for bit 1 is P1, so the photocurrent for bit 1 is that, and for bit 0 is just 0 because P0 is 0, right? And cosine phi is some constant because again the information is encoded in the phase, in the amplitude, and so this phase is not varying between the bits, right? So, for example, if the phase is locked here, we can just say this phi is 0 and this cosine phi factor is 1. Okay, so okay, so then you can see that so again your baseband current here, right? So basically it has a signal component and a noise component, right? And the signal components has a high level I1, low level I0, and there is noise on both of them, right? So again, it looks something like this. So you have I1 here, I0 which is 0, and then you have noise on top of it, right? So this is the same sort of scenario we had for IMDD, right? We had the high and low levels, and then we had noise on for each, and then so we assumed some random distribution for the noise, right? And we set some threshold and say, okay, the probability for an error is that if bit 1 is sent but I detect bit 0, so I see what is the area under this probability distribution which goes below my threshold. Okay, so same thing is done here, right? So we're getting two levels of current. We can set some threshold here and decide bit 1 if it's the detected current is above the threshold and bit 0 is below. Okay, so then basically again we can assume this noise to be a Gaussian random variable. Right, so again, so you could take like variance sigma, standard deviation sigma 1 for bit 1 and sigma 0 for bit 0 in just general case. But here, as you know, because of the local oscillator, we go into the short noise limit, right? And in the short noise limit, basically the short noise is coming basically from only the local oscillator we saw, right? Because the local oscillator power is much higher than the received signal power. So basically both sigma 1 and sigma 0 will be the short noise from the local oscillator for this case. Anyway, so basically we do the same exact thing that we did, right? So we calculate the area under this. So we get the same expression for the BER. If you assume a Gaussian random variable here, so this complementary error function of this Q factor, right, where Q is again defined as sort of something like the signal to noise, so the difference here in the signal levels I1 minus I0 divided by the sum of the noise currents. Okay, and so again, so if I0 is 0 here, and then sigma 1, so basically sigma 1 and sigma 0 are the same, which is basically the local oscillator short noise. And so you know the expression for the short noise current, right? So it goes as the local oscillator power and the bandwidth. Right. So basically, for this case, So I0 will be 0 and sigma 1 is equal to sigma 0. So Q basically, right? And so I can write this as half of the square root of the SNR, the electrical SNR that I get for bit 1, right? So SNR again, the electrical SNR here, so for bit 1 is the current, square of the current that I get divided by the noise variance current, right? Okay, so proportion to the square root of the SNR, which you've seen before. Okay, and this SNR we had derived in the last class, right? So this SNR again using so for coherent detection we had computed, so we go into the short noise limit and we computed the noise current here and then the photocurrent that we get, and recall that from the last class, right? So for coherent detection the SNR noise limit we could write as 2 times the quantum efficiency of the detector times the number of photons per bit, right? So again, so if you're looking at the SNR for bit 1, so then NP here is the number of photons in bit. Because of course for ASK here for bit 0 we are not sending any photons at all, right? So this expression we had derived in the last class. This is basically in the short noise limit. Okay, and so this was for we call heterodyne detection. So if you have homodyne detection, then you have an extra factor of 2, so this is 4 times, right? Because homodyne detection gives you a 3 dB enhancement in SNR compared to heterodyne. Heterodyne. Okay, so basically we can substitute this expression for the SNR in terms of photon number into here to get the Q factor in terms of the photon number, right? And then if you substitute that into this expression, we can basically get the BER in terms of the photon number of photons that we send per bit or in bit. Right, so this basically comes out to be okay. So this is the expression for the BER as a function of the number of photons that I receive per bit for ASK heterodyne synchronous detection. Okay, so again we can say, okay, let's say if I want a BER of 10 to the minus 9, how many photons do I need per bit here? See, again, we can assume like an ideal detector for now. So this is, let's say, eta is 1. Okay, so you can see that for ASK modulation with synchronous heterodyne detection, we can obtain a 10 to the minus 9 BER with only 72 photons per bit received. Okay. By the way, can you guys still see the board and hear me? I'm getting some notification here that there is some bandwidth issue. Is the audio and video clear? Was it not visible before? Did you guys miss this discussion? Yeah, I'm getting some. So message keeps flashing that the bandwidth is not enough. I don't know why. I'm connected to the institute network only. Uh, anyway, did you follow the discussion so far, or? And the recording should have. Recording should be complete. I don't think that should have any interruption. So if in case you miss something and you want to go back and check, you can check the recording. Okay, so yeah, so here basically we obtain a sensitivity of about 72 photons per bit. Right, again, so compare that to when we were operating like in the thermal noise limit, about 1000, 2000 photons per bit. And we saw that, for example, if you use an optical preamplifier before the detector, we can improve the sensitivity and go down to maybe 200 photons per bit. You can see here with coherent detection, we can do even better, right? 72 photons. And so if you do homodyne, you get a 2 times enhancement in this SNR here, right? So you get factor of 2 here, or a factor of square root of 2 in the Q factor, right? So for this is now by 2 instead of by. And homodyne by definition is synchronous, right? We don't have, you saw that basically, since for homodyne means you need to recover the carrier and the phase because you need to lock the local oscillator's carrier and phase to the received signal. So it's by definition synchronous. Homodyne, there is no asynchronous homodyne. Anyway, so because of this enhancement of 2 in the SNR, so now for the same BER 10 to the minus 9, you need only half of this, so 36 photons per bit. So basically for homodyne, we call SNR was 4 times bigger. Okay, and we had done a discussion when we were discussing the just IMDD link, so direct detection. So we were just theoretically discussing if our right, which typically is not the case. If you use a pin photo detector, then you are in the thermal noise limit. You can use an APD to try to go into the short noise limit, but that actually adds some. If you're truly in the short noise limit, then basically, actually, this was the same expression that we got for IMDD if you could noise, which was, of course, practically not realizable. Give you higher gain and take you to the short noise limit. They actually add extra noise on top of the short noise. But here you can see with coherent detection, we can actually realize that sort of limit. Okay. And not only that, we can realize that we just start. Okay, so if you look at it in terms of power, so if I see, so the power per bit here, the power received power T1, if I write as the number of photons times S2 times bit rate, then so again, if I assume wavelength 1.55 micron, even assume a quantum efficiency here now, let's say 0.8, and let's say a bit rate of 1 gigahertz or 1 Gbps. Then this T1 comes out to be, so for 36 photon, you put 36 here, this comes out to be about 6 nanowatts. For this heterodyne, it will come out to be, of course, twice of that, so 12. Okay, so you can see that the receiver sensitivity is now gone down into the nanowatts level. Typically, we are operating like in the microwatts level. If you are, let's say, in the thermal environment with standard bit detectors, but with coherent detection, now we can sort of improve the sensitivity by 20 dB roughly, right, or even more sometimes. Okay, so this basically discussion shows you for ASK or just intensity modulation, how going to coherent detection gives you a sensitivity enhancement compared to direct detection. Right. Now let's discuss other modulation schemes. So, for example, we have phase shift keying. So now, of course, we can't. Okay, so again, so if we start from this expression here. So now the information is encoded in the phase here, right? This amplitude IP is the same for both bit 0 and bit 1. What changes is this phi p. Right? So okay, so now this phase basically, for example, is 0 for bit 1 and pi for bit 0. Right, so then you can see that, so this baseband current here, so the current for bit 1, so if I put pi equal to 0, so cosine phi is 1. So this is IP by 2. Whereas for bit 0, if I put phi equal to pi, then this is minus 1. So this is minus IP. Okay. So now actually you get a negative current for bit 0 as compared to bit 1. But the magnitude is the same. Right? And this negative current is just coming from the phase flip. Okay, so now again, if you look at this Q factor here, so now we put I1 and I0 as this here, and again sigma 1 sigma 0 is again just the local short noise from the local oscillator. So then this Q factor for the PSK will become 2 times I1, right? Because I0 is minus I1 divided by again 2 times sigma 1 because sigma 1 is equal to sigma 0. So this becomes I1 by sigma 1, right? As compared to half of I1 by sigma 1 for ASK, right? So this you can see basically now is square root of the SNR. Right, and So now it doesn't matter. I don't need to write bit 1 here because the SNR for bit 0 is the same and also sigma 1 and sigma 0 is the same. So this could be the SNR for bit 0 or bit 1, right? Or the average SNR per bit, doesn't matter. Okay, so you can see that so for PSK, the Q factor is twice what you get for ASK for the same SNR, right? So that would mean that from this expression for the BER, for the same SNR, I will have a lower BER for PSK as compared to ASK, right? And again, this SNR, if I have heterodyne detection, then so this is 2 times the photon number for heterodyne detection, right? And 4 times the photon number for homodyne. Okay, so and now again, this NP is the average number of photons. So the number of photons in bit 1 and bit 0 are the same because, right? So the number of photons that because the power is not changing, right? We are only changing the phase, so the optical power is constant. So the number of photons, average number of photons is the same as the number of photons in bit 1 or the number of photons in bit 0. Okay. So again, from here you can see that this comes out to be this for PSK heterodyne, synchronous, right? And you have a factor of 2 here for the okay. Compare it to the ASK homodyne heterodyne. You can see that the argument of the complementary function is larger here, right? So for the same number of photons, we get a lower BER, or equivalently 10 to the minus 9. Then for PSK heterodyne synchronous detection, I just need, so NP is 18, right? So again, it was 72 for ASK heterodyne. I'm already down to 18 for the PSK heterodyne synchronous, and if I go to homodyne, then it's even lower, so just 9. Right? So this is actually the best modulation scheme if you can implement it, is the PSK modulation with homodyne detection, gives you the best sensitivity, and which is only 9 photons per bit. Okay, so you can see that this is now at the level of, so remember we were discussing this ultimate quantum limit of photo detection. So when we were discussing IMDD direct detection, we said, okay, if you had an ideal receiver, what is the best sensitivity that I could get with an ideal receiver and direct detection? And that, if you recall, was around 20 photons for bit 1, or if you average over bit 0 and bit 1, I think that, so that was about 10. So this, you can see that, so this is 9, right? So this is at better than the quantum limit, the ultimate quantum limit for direct detection, and also this is actually realizable, right? Because of course this is with quantum efficiency equal to 100%. So if you take, for example, a real detector with quantum efficiency 80% or something, then this will go up to maybe 10 or 12. Right? But nevertheless, so this is sort of the theoretically the best you can do, best sensitivity that you can get to use PSK modulation with homodynamic detection. Okay, and then key we have, which is frequency shift key. Right, so here the signal is encoded in the frequency, right? And remember, the frequency was coming sort of before this, when we had an intermediate frequency, right? And then we converted it to baseband and then had a low pass filter. So now for FSK, basically you have two intermediate frequencies, right? Because so bit 1 and bit 0, your frequency is different. So you'll have basically two intermediate frequencies. So you'll have a omega IF1, which is some omega IF plus delta omega, and then omega IF0, which is some omega IF minus delta. Okay, so now you need two different. So for synchronous detection receiver, you need sort of two parallel blocks of receivers. So you need to recover the. So you need an electrical PLL for this frequency, and then you will need an electrical PLL for this frequency. So it's like two ASK receivers in parallel, right? And sort of do this carry recovery and then beat with the signal and then do low pass filtering. Then basically you get the same current for the ASK, right? So I0 is 0. Okay, and not I0 is not 0, but it's sort of the same as I1, right? It's just that in which arm. So if the output comes out of this arm of the electrical receiver, then you say it's bit 1. If it comes out of this PLL, then you say it's bit 0. But the peak current for both will be actually the same, right? So so compared to ASK, right, we can say that there's a SNR, because for I0 also I get the same magnitude as I1. Whereas for ASK, I only got the signal for bit 1, for bit 0 I didn't get any signal. Okay, and so for FSK it's like two receivers, two ASK receivers in parallel, and I'm getting, so depending on which of these two parallel circuits I'm getting the out signal for both bit 1 and bit 0. Okay, so that's another story. We can't use this kind of formula here because we use this formula when we have only one output and then we decide based on the level. Here we actually have two parallel outputs, and depending on which output the current is coming from, we are deciding the bit. Right? So just by that argument, we can say this without we can't use this formula here, right? But we can use the same formula here to find the BER if we relate the Q to the SNR for ASK. Right, like that. And so basically, again, so this will be 4 times the number of photons for heterodyne, because so for ASK we had 2 times, multiplied by 2 will be 4 times, and it will be 2 times 4 or 8 times for the so actually there is no homodyne for FSK, right? Because we are actually varying the frequency, right? Homodyne by definition only makes sense when if you have a fixed carrier frequency, right? And your local oscillator is much to that frequency. But here I am actually anyway varying the frequency, so I will always get an AC signal depending no matter what frequency I fix the local oscillator at. So okay, I hope that is clear. Okay, so anyway, so we put this expression for the SNR into the Q and the BER here. So then BER will come out to be okay. So this is for FSK heterodyne, or FSK by definition heterodyne. Okay, so again for 10 to the minus 9, this comes out to be 36 number of photons per bit. And now again for FSK, bit 0 and bit 1 both have the same number of photons. Okay, so basically, yeah, we can see how the 3 different modulation schemes compare, right? ASK, homodyne heterodyne, PSK, homodyne heterodyne, and then FSK, which is only heterodyne. So we can sort of combine all of this and just see, sort of compare in a table. Okay, so for synchronous receivers, so let's say here are the modulation format, and so this is the receiver sensitivity, number of photons per bit 1, so number of photons in bit 1, and then we can also look at the average number of photons. So this is average number of photons per bit across both bit 1 and bit 0. Okay, so here we had ASK if we had heterodyne detection, then this was 72 photons, right? For this was bit 1, right? And so for ASK in bit 0 we are not sending anything. So if we average over a long bit stream which has equal number of bit ones and zeros, then the average number of photons per bit I need is half of this. So now if we have homodyne, then this is half, right? And this is also now half. If we have ESK heterodyne, right? So PSK heterodyne from here you can see this is 18. But for PSK now, bit 1 and bit 0 have the same number of photons. So the average is the same in bit 1. We have PSK homodyne. This is 9 and 9. So, and now if you have FSK, which is by definition has to be heterodyne. So this came out to be 36 and 36. Okay, and so now we can compare this to direct detection. So these are coherent detection schemes. So now if we had an IMDD, simple IMDD link, So a practical case of thermal noise limit. Then this is typically around 2000 or an average of 1000 photons per bit. Okay, if we take the best case scenario that is possible for IMDT, so the quantum limit of photo detection, if we had an ideal detector, the best that you can get for IMDT, so this was about 20 here and 10. Okay, so this is of course a theoretical calculation. It's not practically realizable so far. This is practically what we get with direct detection. You can see by going to coherent detection, we can reduce this by almost a factor of 100. Right? So with PSK, you can see you can reduce by a factor of 100. With others, maybe a little bit more, but definitely an order or 2 orders of magnitude lower than IMDT. Okay, of course, that comes at the cost of receiver complexity. Right? So we saw that for coherent detection, the receiver is much more complicated. Not only do you need an extra optical source, a local oscillator at the receiver, then you also need some more complicated receiver electronics. But if you can implement all that, then you can get a very big sensitivity enhancement. Okay, so that's the case for synchronous receivers. We can do similar for asynchronous. So recall asynchronous receiver was much simpler, right? We use this envelope detector, which you can typically build with a simple RC circuit. So no need to do carrier recovery using a electrical PLL or something. Okay, so but the price that you pay was that the baseband current had both the quadratures of the noise, right? So the price we paid for the simplicity was that, so the baseband current finally we get, so it has the in-phase component here plus the quadrature phase component and the noise contributed by that also. Okay, so for the synchronous, recall, so this was just the first part, so this was just that, whereas for asynchronous now we have both quadrature components. Okay, so here for the synchronous case, right, we have a signal part of the current and then a noise part which adds on to it. So this is like an additive noise, right? So it's easy to model, and then if we take a Gaussian random variable here, then basically the analysis again is similar to what we did for the IMDT. But here, because now the expression is simple, now you can see the noise is adding at 2 different places, and then we are taking square and square root also. So for example, if you take Gaussian random variables for this I in phase and quadrature phase noise currents, then the total noise current for this baseband current will not be Gaussian, right? Because like I'm taking some function of a Gaussian random variable, so the noise statistics of this composite expression will not be Gaussian anymore. Okay, so the analysis is not straightforward now, but one can actually do the analysis, right? So assume we have Gaussian random variables here, and then try to compute what is the random statistics for this expression using sort of advanced statistical techniques, but which is beyond the scope of the course here. So we'll skip the complicated calculation to calculate the SNR and Q factor and the BER for asynchronous receivers. But we'll just discuss the final results. So similarly, like for the synchronous, we can consider the three different modulation formats. Okay, so of course, we have only heterodyne detection for asynchronous because, again, by definition, homodyne has to be synchronous, right? So asynchronous only works for heterodyne detection. So we have only now. So the modulation format, and then again we can look at the sensitivity in number of photons. Before that, so here, if you recall, so the expression for the for this case, for the synchronous case, the expression for the BER was something like error function of the square root of the photon number with some factors here depending on the different modulation scheme, right? So either divide by 2 or 4 or multiplied by 2 or something, right? So it was, I can write some constant A times eta times photon number. So that was the expression for the BER we got in this case. In this case, of course, we won't get the same expression for the BER in terms of the SNR or the photon number because so this again recall came from the integration of this Gaussian function beyond some limits, right? So there is a question: what will be the distribution of this baseband current? Will it be chi-square? I'm not sure, but it might be, but I'm not sure. I think the book has a discussion on what the exact distribution would be, and it has references to the research papers which have dealt with it. So look at the textbook for. I don't recall right now what the distribution of the baseline current would be, but chi-squared maybe sounds right. But check the textbook. Okay, so now if you look at the expression that we get for the BER, so the expression for the BER that you get comes out to be exponential actually. So again, we have heterodyne only for asynchronous, so it could be again ASK, you have FSK, or we can look at, right, which was a more practical case of the phase shift keying, where we look at the differences in the phase of consecutive bits, and we saw how we could implement an asynchronous receiver for that just by having 1 bit delay and then taking the product of the two. Okay, so if you look at these modulation schemes, then the BER expression here comes out to be exponential with the photon number, which is actually similar to what you get here actually. So recall when we discussed this quantum limit of photon detection, we assumed Poissonian statistics, and then so for here we had got an expression like this, exponential. Okay, so for all these cases we get error function because we assume the statistics to be Gaussian. For this quantum limit, recall we had assumed the statistics to be Poissonian, and then got this expression. So here, of course, it's not Poissonian; it's still some continuous distribution. But the final BER expression that we get comes out to be exponential. I think there are some approximations also involved because the integrals that you will get, I think, are not analytically solvable, and then you have to make some approximations to actually finally get to the exponential form. But again, refer to the textbook and the references given there, and if you're more interested in how you get from here to evaluate this. Okay, so again, just like for here, there are differences in the multiplicative factor with the photon number. So here we have by 4, here we have by 2. Okay, so now again we can say, okay, what is the number of photons I need for BER 10 to the minus 9? So I could have a receiver sensitivity here for NP. So now this is, NP here is the number of photons in bit 1 again. And then the average will be average over bit 0 and bit 1. So again, so if you put for BER equal to 10 to the minus 9, so you equate this expression equal to 10 to the minus 9. Again, assuming eta equal to 1, so you get 80, about 80 here. For ASK, the average is half of the number of photons in bit 1 because bit 0 has no photons, so here you get 40. For FSK, this comes out to 40 because there's a factor of 2 here. Average is equal to the in bit 1 because for FSK we have the same power. And then for DPSK, it's the best. 20. Okay, so you can see that actually with asynchronous receivers also, which are much simpler to implement, recall, compared to synchronous, right? You can get, so for example, this DPSK asynchronous is quite simple to implement, right? Because you don't need very good phase noise in the transmitter. You just need phase coherence to be more than at least 2-bit duration, right? So you don't have very stringent requirements on either the transmitter laser or the local oscillator laser, the phase noise of the local oscillator. And also the synchronous receiver, you just need, we saw that, so here we just have a 1-bit delay, we multiply and then have a low pass filter. It's very simple. So you can see that with that, you can get a sensitivity of 20 photons per bit, which is, you can see that is quite compared to the best of the synchronous receiver case also. Right? Of course, the best that you can do with synchronous receiver is 9. So maybe a factor of 2 better than what you can do here, but again, this requires much more stringent requirements on both. So my receiver electronics, my transmitter laser, local oscillator laser, a lot of things, right? So if you look at the trade-off between implementation complexity and the actual sensitivity you get, this comes out to be most viable. Okay, and then we can look at, for example, you can compare all different kinds of modulation formats and detection schemes, right? And plot them on like a BER versus number of photons per bit. So okay, so both of these are on log scale, BER 10 to the minus 3 to 10 to the minus 12. Number of photons here 1 to 100. So you get different curves here, right? Depending on this expression here. So you get different curves for the different modulation formats. So, for example, the best curve here comes out to be for PSK homodyne, right? So you get the lowest BER with the smallest number of photons. And then as you go to other modulation schemes, this curve shifts to the right, like that. Actually, that's okay. So you can see, so basically what you've tabulated here is if we take a horizontal line with 10 to the minus 9, where does it cut the different curves, right? So for PSK homodyne, it will cut at 9, right? And then for these are for others, so this one is, for example, synchronous PSK heterodyne, and this dashed line is asynchronous PSK heterodyne. Right, so you can see that so that cuts at 18 for the synchronous and 20 for the asynchronous. PSK. Right, and then we have FSK here, again synchronous and asynchronous, which cuts at 36 and 40. And finally, we have ASK. So this is again synchronous and asynchronous. Okay, so you can see that PSK gives you the best sensitivity, followed by FSK, followed by ASK. And then for each case, homodyne is the best, or synchronous, followed by asynchronous heterodyne. Okay. Okay, so now just like in the IMDD case, right? So we got this sensitivities depending on the noise at the receiver. Similarly, here also we only the sensitivities we have computed only considering the noise at the receiver. But of course, there are other factors that could lead to degradation in the sensitivity, right? Which, for example, we measure by a power penalty, right? How much extra power we need to get the same BER. So we have discussed a few mechanisms for power penalty in the IMDD case. Similarly, we can discuss a few important ones for the coherent receiver case. Nice. So in addition to receiver noise, there are some other factors which could cause degradation in the sensitivity. So for coherent detection, of course, we are beating these two signals, right? The local oscillator with the incoming signal. So, and we saw basically, so phase and frequency stability is of course very important. So one thing you can imagine that will affect the performance is phase noise, right? So both sort of in my source or transmitter laser and my local oscillator, right? So phase noise on each, because I'm beating these two, phase noise in each of these two will, of course, degrade my performance, right? So far in our analysis, we assume sort of perfect sine waves for the incoming signal and the local oscillator signal, right? So again, if you look at sort of this beat current that we get, that depends on the difference in the phase of the signal, incoming signal and the local oscillator, right? So if there are some phase jumps here, either in the signal or in the distort my signal, right? Add noise. And you know that basically a laser, so it's a sine wave for some time, and then there is some abrupt phase jump, and then it's sine waves for some time, and then phase jump. So there are every once in a while there are phase jumps, right? Which gives me the finite line width of the laser, right? So basically this drift, so this is okay, which can be written as the drift in the frequency of the laser multiplied by the detection time or measurement time. Okay, so let's say I have 10 gigabit per second data rate and I'm measuring 10 billion bits. So that would mean a total measurement time of 1 second. Right? So this frequency drift, we can just say, is sort of the sum of the line width of the source and the local oscillator. Right? So this is the spread in the frequency of the source. This is the spread in the frequency of the local oscillator. So multiplied by time, that is the spread in the phase. Okay, and basically you can see that the important measure is that, so if I'm looking to measure the phase in a particular bit, right? So let's say P, I want to measure the phase precisely for 1 bit or 2 bits, but the phase, so this drift here, right, over 1 bit period, right, should be very small. Otherwise, I can't recover. I can't. Right? So this delta nu times t bit period. So the drift in the phase in 1 bit period, or I can write this as sort of the total line width divided by the bit rate also, because TV is a function of t. So typically, for figure of merit, this is typically kept below 10 to the minus 3. Okay. So the phase drift here is below 10 to the minus 3 radians, then I can, with a precise, I can measure the phase here precisely. Okay, and this typically number is coming again, if you again, we're not going into the detailed calculations. So from this phase drift, you can try to calculate a power penalty, and to keep the power penalty below 1 dB as it's typically required, you want this phase drift in a bit period to be below 10 to the minus 3. Okay. So typically, if you plot, for example, the sensitivity, so the number of photons required per bit for BER 10 to the minus 9, number of photons per bit for minus 9. So 0, as a function of this total line width divided by the bit rate. Okay, or in other words, if I look at the interference, the intermediate frequency when I beat the source and the local oscillator, I get an intermediate frequency signal, right? If I look at the signal, this is a megahertz for a bit rate of 1 gigabit per second, right? So it's just a different way of writing this, right? If I put B equal to 1 Gbps, what is delta U? So this is 1 megahertz here, 10 megahertz, 100, so on. So again, we get different curves for different modulation formats. We won't go into the details of the calculations, but to see how they vary. So if you look at the best in terms of sensitivity that we got was the PSK homodyne. So that goes like this, but it also scales the worst with phase noise because in PSK homodyne, basically we are encoding information in the phase, right? And PSK homodyne is absolute PSK, it's not the differential PSK, which means we need very good phase stability, right? Absolute phase stability over many bits. So you can see that when your line width is much smaller than the bit rate, then it's very good. Okay, so here is starting from this number 18 that we had. But then very quickly it starts rising with increasing line width. Whereas if you look for the other modulation schemes, so for example, if I look at ASK, it of course starts higher than the PSK, right? But it scales much slower, like that. Okay, so you can see that roughly once you go to a line with more than 1% of my bit rate, then actually ASK becomes better than PSK. So this is ASK heterodyne asynchronous. Okay, so again, going back to the point that PSK homodyne can give you the best performance, but you require very stringent parameters, like for example, extremely low line width lasers. So you can see that for a 1 Gbps bit rate, the line widths of both your source and local oscillator have to be much below 1 megahertz. And then you get similar curve for sort of FSK, but slightly higher than ASK. Okay, so if you have very good equipment, the best lasers, the best sort of detectors, phase lock loop, etc., then you can get this best performance of the PSK. But if you have sort of more economically viable equipment with you, then you can see that ASK is probably easier to perform. Okay, so that's the phase noise. We also have intensity noise, or specifically relative intensity noise in the laser, right? So again, because we are beating these two, so the incoming signal with the local oscillator, and we saw that the photocurrent that we get is sort of scales as the square root of the product of the signal and the local oscillator powers, right? So any fluctuation or the noise in the powers will give me a noise in the current, right? Just like in direct detection also, right? Any noise. So we saw that relative intensity noise gives me a power parity. So similar will be the case for coherent detection also. And in this case, basically the most, the main source of noise will be the local oscillator, because recall that we set the local oscillator power to be actually much larger than the signal power, received signal power, right? So, and we know that the mean power, optical power. So basically, mostly the local oscillator intensity noise is what contributes. Okay, so just like in the IMDD case, basically we can include the RIN noise in my total noise current, right? So I can include short noise, thermal noise, and then also RIN noise, right? So we saw for coherent detection, short noise basically mostly comes from the local oscillator. RIN noise will also come from the local oscillator. Okay, doesn't depend on either the optical power or the local oscillator power. And typically, the short noise is much bigger than the thermal noise because we use a high local oscillator power. But just for a complete analysis, we can keep the thermal noise current also. And so, what is this noise current of the RIN? Recall this we had discussed when we were discussing the direct detection receiver. So, this is responsivity times the local oscillator power times this factor, which is basically the giving me the RIN of the laser. Okay? So recall this factor Ri was defined as, so Ri square was basically the integral of this relative noise intensity spectrum within the detector band. Right? So this is like the total. And so if we assume some average RIN over the detector bandwidth, so it's that average RIN times the detector bandwidth. Right, so for example, this will be like some minus 140 or minus 150 dB per hertz. So again, this is assuming, so your actual RIN spectrum probably has some peaks here, but let's say we integrate all this and then assume a flat level up to the detector bandwidth. And so this is the average. So we have expressions for all of these, right? So we can write the SNR again. So the SNR, so the mean square current will go like this, right? So recall, so the photocurrent was something like this, square root of responsivity times local oscillator power. So I square will be responsivity square, signal power, local oscillator power. Okay, and then I put a factor of half, assuming again, let's say it's heterodyne detection, so there's an AC current, so I put a factor of half, so I get 2 here instead of 4. So again, if you had homodyne, then you need to put a 4 here instead of 2. Okay, and then in the denominator, the total noise current. So the first term will be the short noise current, which is again coming from the local oscillator, right? So I can write it like this. I can also include dark current. Typically that is negligible, but could also include that, right? And then Thermal noise current again will depend on the electrical circuit parameters like the load resistance and the noise figure of the electrical amplifier, etc. But so there's some thermal noise current here. And then the rim noise, again, I can write like this. So I square will be this times the rim times theta. Okay. So I can write the SNR like this in terms of the local oscillator power, right? So so this SNR is now a function of the local oscillator power, you can see, right? It's coming in the numerator and the denominator, right? So as I vary the local oscillator power, the SNR will change in a non-trivial manner. So typically, if we so far we neglected the rim noise, and so we just had this, and as we increase local oscillator power, basically the first term will become dominant over the second term, and then we go into the short noise limit where the local oscillator powers cancel in the numerator and denominator. But now if you have rim noise also, you can see that scales are the square of the local oscillator power, right? So as we are increasing the local oscillator power, this term will actually scale very fast, right? And my SNR won't improve anymore. After some point, it will actually start degrading. Okay, so again, I can define a power penalty saying so. Right, so let's say for a particular BER, right, 10 to the minus 9, I need some value of the SNR, right? Depending on the modulation format, right, we derive these expressions. So for given BER 10 to the minus 9, I need a certain Q factor or a certain photon number corresponding to a certain SNR, right? So without any rim noise, you can see that I can achieve that SNR at some particular signal power, right? So let's say we first fix our local oscillator power, right? Then we will obtain the required SNR at some particular signal power. Now, if you include rim noise, you can see that I will require more signal power because my noise has got in the denominator. To get the same SNR, I have to increase my signal power, right? So the power penalty I can define again as dB will be 10 log 10 of so the PS required for a particular SNR with for a particular rim value divided by the signal power required for that SNR with no rim. Right. So how much more power, signal power I need because of the rim noise? That's the power. Right. So you can see that we can calculate from this expression here, right? So we put rim equal to 0, and then we put rim equal to whatever value we have. So we can plot this power penalty as a function of the rim, right? In dB per hertz here, and we'll get different curves depending on the local oscillator power, right? So for a given rim, of course, it also depends on the what power of the local oscillator I'm using. We'll take the typical range of the rim from minus 160 to minus 130. And so we get different. So the effect of the rim you can see is the least when the local oscillator power used is small, right? If we use a smaller local oscillator power, then the effect of the ring is small because it's multiplied by PLO square. As we increase the local oscillator power, the effect of the ring increases. Okay? So we get a curve like that. So if this is local oscillator power of 10 microwatt, then if I increase, so this is local oscillator power of 100 microwatt, and then this is local oscillator power of 1 milliwatt. Okay, so you can see that the power penalty is increasing. For a particular ring, the power penalty increases with increasing local. Because of this. Okay, so these curves again, so you have to assume some responsivity here. So that's assumed. So this is 1 amp per watt. Okay, so you can see that, yeah, you can get significant power penalties, right? So 160 minus 160 dB per hertz is sort of the best lasers that you can get nowadays, the most expensive ones. Typical, you'll have between, let's say, minus 140, minus 150. So you can see that, for example, if you use 1 milliwatt local oscillator power, the power penalty can be really large. So the ring noise actually can be a big problem.
So,
Yeah.
Can you extend the time?
Oh yes, thank you. Just did that. Yeah, thanks for that. Right, so you can see that for typical values of the ring that we have for typical semiconductor lasers, it can be actually a big problem. Okay, so what is there a way around this? So there is actually a way to eliminate the effect of ring noise altogether, which is to use what is known as balance detection. Okay, so far in this discussion of coherent detection, we sort of only discussed what is known as unbalanced detection. Okay, which means we are using only one photodetector. So we beat the right. So what we do is basically, so we have beam splitter, or let's draw it in a fiber beam splitter. Right. So let's say we have a fiber coupler here, 53 dB coupler. We have a signal coming in here. We send our local oscillator from the other port. And basically, we just take the output from one port and then this photodetector and then measure the photocurrent. That's what we've been discussing so far. Right? So this is called unbalanced detection. What you can do is, because of course this power coupler has another port also, right? So it doesn't matter, you could use fiber, or even in the free space case, right? You have 2 input ports and 2 output ports. Right? So you could detect both the output ports. So in balance detection, what we do is we also put a photodetector in the other output port, okay, and then get photocurrents from both. And then what we actually do is subtract the photocurrents from both ports. Okay, so for example, you could have like an amplifier circuit here, which amplifies the difference of the two photocurrents here. Okay, and the final current that I get, the signal current, so I call this maybe I plus and I minus, is the difference of these. Okay, so what's happening here? So we call it, this is a 50-50 or 3 dB coupler. There are actually phase, so the fields here add up with some phase shifts, right? So for example, so if this has some amplitude A, so mod A square is yes, or this has some amplitude ALO, right? So in one of the ports, basically what you get here, so the fields add up in phase, right? Or I mean, to be more precise, I could add like the 1 by square root 2 here. And in the other port, they add up with a phase difference of pi, right? So recall our discussion from the previous fiber optics course when we discussed it. So there's a phase, fields add up with different phases in the two ports. Okay, so and so basically the power detected will be the mod square here, right? So you can see that, so I plus will be something like responsivity times. So I have a mod A square, so that's signal power, then I'll have mod ALO square, so local oscillator power, and then the cross term, the plus sign. So, right, and I minus here will be now responsivity again, so I'll get the DC terms. And then the cross term will have a negative sign because of this. Okay. And now when I take the difference, you can see that the DC terms will actually cancel out, right? And I'll get something which is proportional to just the cross term. Okay. So firstly, one advantage that you directly get is you directly cancel out the DC term, right? Because this DC term can actually be very large because of the PLO, right? So rejecting this DC term is actually, otherwise you have to use some DC block or AC coupled detector, right? So to reject this DC is also important and not so straightforward. But in this case, you can see that the DC is already rejected. Okay. Because if you have too large a DC, basically that can saturate your detector, such that you don't see the variation of this, the signal anymore. Okay, so it's important to reject the DC. Anyway, so this automatically does that, right? And not only that, so now because it's rejecting these the signal and the local oscillator power, right? It will also reject the noise along with these, right? So if I have any noise in the optical power of the signal or any noise in the optical power of the local oscillator, you can see that that will also get cancelled out, right? So it doesn't matter if PLO is a constant or if it's varying slightly, because I'm getting the same value at both the photodetectors, and then subtracting, they get cancelled. Okay, right? So any fluctuation in the power here, basically half the fluctuation will come here, and the same fluctuation will, half the fluctuation will go here, half the fluctuation will go here, and when you subtract, the fluctuation gets cancelled out. Okay. So you can see that this basically you can cut out the intensity noise by using this balance detection. Okay, so that seems great, and this is true, but not entirely. Okay, you reject all the noise up to when you reach what is known as short noise or the quantum noise. Okay, so again, this noise in the optical power can come from various reasons, right? Technical noise sources like temperature fluctuations, mechanical fluctuations in the cavity, drifts in the current into my laser, etc. Right? So there are a lot of technical noise. All of that will be cancelled out. But then there is some quantum noise, right? So again, we saw that the optical power here is composed of photons which are arriving randomly, right? And this random distribution is some Poissonian distribution, and that is completely random given by laws of quantum mechanics. Okay? So that the ultimate short noise in the optical field that won't get cancelled out. You can see why, because so now assume you have a random stream of photons coming in. So randomly some of them will go here and others will go here, right? If you split half. Basically this cancellation was working because any fluctuation here, I split it into half here and half here, right, and cancelled out. But if you're talking, I either have to go up or down. I can't split a photon into half and send it up and down. Okay. So basically what is happening is this random stream of photons, some of the photons go up, some of the photons go down. So you can see that now when you subtract, they won't get cancelled out, right? Because the photons, the time stamp of the photons here will not be the same as the time stamp of photons here. Okay. So the short noise, so basically you cancel out all the technical noise, and what is remaining here is just the short noise in the optical field. That is the minimum level of noise you're left with in this balance detection. Okay. But that's still a great improvement over, right? So the short noise limit is somewhere like towards here. So the typical range you have in the laser is still above the maybe, I don't know, I don't remember the exact, probably it's 10-20 dB below still here. Okay, so you're still well above this ultimate short noise that you can get to with balance detection. I think that's maybe 170 something, the short noise. Okay, but so you can basically remove all the noise, technical noise above the optical short noise using balance detection. Okay, the price you have to pay, so you have to use an extra photodetector and then this subtraction and application.